Assalamu alaikum, dear students. Let's now move to the next topic, which is the BCS theory of superconductivity. Now, this theory is based on modern concepts using high-level quantum physics. In fact, it is out of the scope of our level at this moment to literally derive this theory, but today we will talk about the essential features of the conclusions of this theory. This theory was presented by three famous physicists, Bardeen, Cooper and Schrieffer, in their classical paper in 1957. They won the Nobel Prize by presenting this theory. Now, let me give you display the page of the book by Ali Umar from chapter number 10, in which we will discuss and read through this theory. So it is page number 513 from this book, rather page number 511. Right at the bottom of this page we have the article Theory of Superconductivity. In fact, this is the BCS Theory of Superconductivity. So let me go through the text, and I will keep giving you the remarks alongside to understand this theory. Okay, the BCS theory has now gained universal acceptance because it has proved capable of explaining all the observed phenomena relating to superconductivity. So, starting from the first principles and employing a completely quantum treatment, the theory explains the various observable effects such as zero resistance, the Meissner effect, etc. Because this theory is so steeped in quantum mechanics, one cannot discuss it meaningfully without using the advanced quantum concepts and mathematical techniques. Therefore, in the interest of simplicity, let us instead give a brief qualitative conceptual exposition of this theory. Okay, this theory also includes the concept of the normal and superelectrons. Now consider a metal in which the conduction electrons lie inside the Fermi sphere. Suppose that two electrons lie just inside the Fermi sphere, as shown in figure 10.15 here, and these two electrons repel each other because of the Coulomb interaction of being both negatively charged. But this Coulomb force is reduced substantially on account of the screening due to the presence of other electrons in the Fermi sphere. After the screening is taken into account, the interaction between these two electrons disappears almost entirely, although a small repulsive residue force persists. However, something new may occur, we can suggest here. Suppose that for some reason the two electrons attract each other. Now, that is a novel concept here, and we will give you the reason for this. So it was Cooper who showed that these two electrons would then form a bound state provided they were very close to the Fermi surface. Now this is very important because in bound state electrons are paired to form a single system and their motion are correlated. So what we are going to suggest here as a conclusion of this theory, that these two electrons near the Fermi surface, they are paired up, which we call the Cooper pair. So there are several Cooper pairs. So instead of considering the single electron, we will consider these Cooper pairs. Each electron just near the surface is paired up with another electron diagonally opposite. So we have shown such two electrons, number 1 and 2 here. The pairing can be broken only if an amount of energy equal to the binding energy is applied to the system. Okay, our two electrons are called a Cooper pair. The binding energy is strongest when the electrons forming the pair have opposite moments and opposite spins. That is K upward and minus K downward. It follows therefore that if there is any attraction between them, then all the electrons in the neighborhood of the Fermi surface condense into a system of Cooper pairs. Now, these pairs are in fact the superelectrons discussed in section 10.5 and 10.6, and the binding energy correspond to the energy gap introduced in section 10.5. So in figure 10.16 we present the detail of the configuration of these two electrons 1 and 2 making the Cooper pair. So here you have to focus very carefully on what is being stated, what is being shown. We have been talking about the consequences of electron attraction. But how does this attraction come about in the first place? That is a question. In conductive materials, it results from the electron lattice interaction. So we will not just consider these two electrons facing each other, but we will involve the local lattice structure in between these two electrons. So let us attach this lattice structure on the electron number 1. Suppose that the two electrons 1 and 2 pass each other. Because electron 1 is negatively charged, it will definitely attract positive ions towards itself And this is the electron lattice interaction. So the electron number 2 does not see the bare electron 1, but it will see this electron 1 along with the lattice surrounding this electron. So we can say that electron 1 is screened by ions by the lattice contribution. The screening may greatly reduce the effective charge of this electron. In fact, the ions may over-respond and produce a net positive charge, as shown in this figure. If this happens, then electron 2 will be attracted towards electron 1, instead of being these two electrons repelling each other. Okay, they are repelling, but now this lattice involvement surrounding one electron, making it a positively charged for the electron 2, so they will have this attractive interaction. So this leads to a net attractive interaction as required for the formation of the Cooper pair. The ions over-response may be understood qualitatively. Since electron 1 is near the Fermi surface, its speed is great. At the same time, the ions, because of their heavy masses, respond rather slowly. By the time they have left and completely respond to electron 1 has left its initial region, at least partially, thus stimulating the overcompensation. One can also reason that this process is most stimulating the overcompensation. So one can also reason that this process is most effective when electron 1 and electron 2 move in opposite direction. So this is a small question. Why? The answer is that these two electrons must have opposite spin for the pairing process. Only the electrons with opposite spin can be paired. Now, in technical literature, one says that each electron is surrounded by a phonon cloud. So the lattice contributions will now be talked in terms of phonons. So we see that there is a phonon involvement in between these two electrons. For example, electron number 1 emits a phonon which is very quickly absorbed by electron 1, as shown in figure 10.17. Next page. You will see when the next page will be displayed. So we have two electrons established an attractive interaction by exchanging phonons. For example, electron number 1 emits phonons which are very quickly absorbed by electron number 2, as shown in the figure 10.17. Since the phonon is involved twice, once in emission and once in absorption, so this attraction between electrons is a second-order process. As a result of this binding between electrons 1 and electron, an energy gap appears in the spectrum of the electron. You know that the lattice interaction always contributes with an energy gap. So there is a slight energy gap which will be produced as we consider this electron-phonon-electron interaction. Let me bring you the next page. Okay, the figure 10.17 is here, which is showing this electron-phonon electron interaction. Right. The states in the energy range and the band gap, which I just mentioned, is shown in figure 10.18. So referring to the diagram, to the figure 10.18, let us now read through the states in the energy range, that is EF minus half delta naught, if delta naught is the energy gap. So this gap exists between the energy levels EF minus half delta naught and EF plus half delta naught. Now this range is forbidden. These states have been pulled both down and up, resulting in a peaking of the density of states just below and just above the gap. Far from the Fermi energy, the density of states for the superelectrons is the same as in the normal matter. Now, the BCS theory gives us the value of this energy gap at zero temperature to be given by equation 10.30 here. Delta naught is equal to 4 h cut omega d e to the power minus bracket 2 over g density of states at the Fermi level into the voltage. This voltage V dash is in fact the interaction we have just mentioned, and WD, which is the Debye frequency, and this factor is coming because the lattice is involved here, and we have already introduced the Debye frequency when we talked about the heat capacity model given by E. Debye. And GEF is the density of states for the normal metal at the Fermi level, and B dash is the strength of the electron lattice interactions. So fair enough, what we are in fact presenting here is the result of the BCS theory, but the description we are giving here is quite reasonable and can be understood easily. The Debye frequency appears in 10.30 because of the exchange of a phonon between the electrons of the Cooper pair. So several interesting results follow at once from this expression. So far was the introduction of the BCS theory. Now let us discuss the various characteristics of the superconductor using this theory. Number A, roughly speaking, delta naught is of the order of h omega d, the latter being the energy of a typical phonon. So this also yields the correct order of magnitude, because when we substitute the typical values of the parameters here, that is h omega d is of the order of 10 to the power minus 27 into 10 to the power plus 13 equal to 10 to the power minus 14 ergs, which is approximately 10 to the power minus 2 electron volt. So when the exponential of equation 10.13 is included, it reduces delta naught to about 10 to the power minus 4 electron volt, and this energy gap is typically the same as we discussed in the London theory, and it is quite in agreement with observation. Now, number B, since omega d is proportional to m to the power minus half, where m is the mass of the vibrating ion, it follows that delta naught is of the order of m minus half. Thus the energy gap and hence the critical temperature decrease as m increases. This is observed experimentally by varying the isotope ratio of the metal and is referred to as the isotope effect. So we see that the energy gap is inversely proportional to the square root of the mass of the atom. So various isotopes will have different masses, and we can introduce here the isotope effect. This effect was observed long before the advent of the BCS theory and was the strongest clue to the fact that the lattice is somehow involved in the process of superconductivity. Number C. The gap increases and so does Tc as the electron lattice interaction V' increases. In other words, a strong V' favors superconductivity. Now there is a very important point which should be noted here. That is, a strong V' favors superconductivity. Now this is plausible statement because when the ions are then attracted more strongly to the electron, increasing the chance of overcompensation occurring. So this result is very curious. On the other hand, because V' is also responsible for the resistivity in the normal state, in which the larger the V', the higher is the resistivity. So we are saying here that a large value of V' favors superconductivity, but on the other hand, a large value of V' increases the resistivity. So we therefore reach the seemingly paradoxical conclusion here that poor normal conductors make good superconductors. So let me repeat this sentence, and you must go to this paragraph very carefully to understand this, that the poor normal conductors make a good superconductors, while good normal conductors are poor superconductors. This is, however, in agreement with the experiment. The former group includes, for instance, lead and niobium, and the later group includes the alkali and noble metals, which exhibit no superconductivity whatsoever, even at the lowest attainable temperatures. So, as we mentioned before, that the alkali and noble metals do not show superconductivity. So here is the explanation for that. The BCS theory shows that the critical temperature is given by delta naught equal to 3.52 kTc. This relation can be tested experimentally because delta naught and Tc can be measured independently. Observations confirm the validity of this relation to a good approximation. Typically, it is found that delta naught is 4 kTc, and table 10.4 gives us the value of these constants for few elemental superconductors. The energy gap decreases with temperature as mentioned in connection with figure 10.12. So this behavior is also derived from the BCS theory, and the agreement with experiment is good. The energy gap can be determined experimentally by any of the several. One involves infrared absorption. If a beam of infrared light shines on a superconductor at very low temperatures, absorption of infrared radiation takes place only when the frequency of the radiation is sufficiently high that a Cooper pair is excited across the gap, that is, H cut omega is greater than 2 delta naught. So this is the experimental observation to feel the energy gap. The gap can therefore be determined from the frequency at which the absorption commences. So since delta naught is 10 to the power minus 4 electron volts, the corresponding frequency lies in the infrared region. So the BCS theory explains the zero resistance property as follows. Once set in a drift motion, a Cooper pair may be scattered only if the Collision mechanism imparts an energy to the pair which is at least equal to 2 delta naught. But at low temperatures, this amount of energy cannot be supplied by the phonons because only very low energy phonons are excited. Thus, the Cooper pair continues in drift motion indefinitely. So, it is the existence of these Cooper pairs of electrons which we called the superelectrons, and they in fact short circuit, and therefore the resistance becomes zero. So this was the BCS theory, and we have seen that it is more comprehensive than the London theory, although London theory is also very successful in the classical range, but this theory is more advanced and is the best theory to explain the superconductivity and all the related phenomena. Okay, so let me stop here, and we have discussed a very successful theory, the BCS theory of superconductivity. So our next lecture will be probably will be the last lecture. So please go through, and I must also suggest that you should go through the chapter on superconductivity from the book by Kittel. After you have gone through Ali-Umar, then you should be able to understand the presentation by Kittel in the chapter on superconductivity. Okay, thank you very much.